Hello and welcome once again to episode 69 of Code Completion. We are a group of iOS developers and educators hoping to share what we love most about development, Apple technology, and completing your code. My name is Dimitri and I'll be your host once again for this episode, and I'm joined today by my fellow completionist, Spencer.
Hey there.
So, I've been using Async Await for quite a bit lately, and Spencer had a bunch of Async Await questions, so we figured what better chance for him to ask them than during an episode, so then everyone can learn along the way. So I guess take it away, Spencer.
Yeah.
It's all on you.
I think, well, we've got a bunch of questions here, and not all of them are mine. So maybe we should just kind of give like a quick recap of like what async await is, and then kind of compare it. Like one of the first questions we have is like, how is it different from Grand Central Dispatch? Another common thing with async await is like, what is structured concurrency and why is it called that? So I don't have a ton of questions. I'm sure they'll crop up as we go through, but let's like do kind of this comparison thing. If like you're new to async await, like I am, or you know, I very much was a week ago. How we have Grand Central Dispatch, so let's start with that. Like, why do we have this compared to it, and what is the difference? I suppose.
Okay, so I guess let's start with what is Grand Central Dispatch, because that will probably help set the foundation for what we're going to discuss. So Grand Central Dispatch is a bunch of APIs that let you coordinate within your code using multiple threads and using multiple cores, so that way you can write higher level abstractions on top of that without like really breaking your brain. The way it does this is it creates what's called a thread pool. So it creates its own threads that it owns. And it coordinates, and it gives you access to these threads through dispatch queues. There are two kinds of dispatch queues. There are global queues, which like there's basically a foundational global queue which takes care of everything, and then you build on top of that by making serial queues, or your own concurrent queues. And serial queues, they process things in a first in, first out order. And concurrent queues, they process things in like anything goes in, anything runs. There's not really much of an order. I think once it reaches a capacity, then they'll actually queue up in a relative order. But there's no guarantees made there. So that's what GCD is. Now, there are some downsides to how GCD works, depending on if you asynchronously dispatch work or synchronously dispatch work to a queue. So as a reminder, like when you say dispatch queue.main.async, you're accessing the main queue, which is a serial queue, which is specifically tied to something special called the main thread. And the main thread is where all of Apple's frameworks assume you are going to be, because traditionally computers didn't really have multiple cores. So like the main thread was an obvious place to just live, and you'll use something called a run loop instead to coordinate everything kind of working together on that main thread rather than multiple threads, which are expensive for reasons we can get into later. So that's why there's a main thread that's special. But when you do .async, it will go ahead and put a task to be run on one of the queues, and then the queues, when they're ready, they'll run your task. That's all great and dandy. Now, there is another way of doing work on a queue, and that's called by synchronously accessing it. And what synchronously means is whatever context you're in, you're going to pause it so that way you can go ahead and finish work that you dispatch somewhere else. So for instance, if you say your special processing queue.sync, then wherever you are, you're going to pause, you're going to finish whatever block of code you just scheduled, and then you're going to continue right afterwards. And this is very convenient when you need to like put stuff together, because sometimes you can't asynchronously just set work to be done in the future. You really need the results right now, and sync is a way of achieving this. Now, that said, sync can get you in all sorts of trouble, namely if you use it in a context that is not ready for it, and then other work gets dispatched to that context or that queue, then GCD will be like, well, my hands are tied, I can't do anything, let me make another thread. And therefore that new work can continue when all the threads are kind of preoccupied. And this will get worse and worse over time, depending on how much you use sync or how many queues you have. Yeah, GCD has a very different set of expectations in mind when you are going to use it, and it's not necessarily used in that way, nor has like the shared knowledge of the Apple development community kind of pushed it in that way. Something needed to change for like to address these new concerns that weren't concerns before. Like the concerns before was, oh, you need to use a thread and you need to use the thread properly. And that's already a big set of troubles that is now definitely not worth it. GCD kind of addresses those concerns, but it brought new concerns with it because people can now go gung-ho and have all sorts of threads all at once, and that is, as it turns out, not that great either.
Right, okay. Yeah, that makes sense. So then async await is kind of the, I guess, evolution of that to address the concerns, or I suppose address those original concerns and address the concerns that sort of then cropped up from GCD.
Exactly, yeah.
Okay, cool. All right. So in the developer app, or well, yeah, I only watch WWDC videos through the developer app now. There's a collection called Meet Swift Concurrency, and the first video is Meet Async Await in Swift, and it's awesome. It gives a great overview of kind of some basic stuff in Async Await, how to use the keywords and everything, and how to make your own functions async await, I guess, compatible. But then the next one is Explore Structured Concurrency in Swift, and that kind of goes into, okay, now we're dealing with not just a single function that is async await, but now we were like looping through things that are using async await. So why is it called structured concurrency, and what is it, I suppose, if that makes sense?
So structured concurrency is actually made up of a term that you might not be familiar with, but you are actually super comfortable with already. And that is the structured part. Because what we are comfortable with as developers is something called structured programming. So you may have heard that like code, once you write it, gets turned into assembly. And assembly does not have all the facilities you're used to. It does not have loops. It does not have if statements. It does not have any of that. It doesn't even have functions, like barely has something that you can link up to as a function in your head. And you have to manage the jumping around of where the processor currently is completely yourself, basically. So that's something called unstructured programming because there's no structure to it. It's just pure chaos. And something that languages like C and eventually Swift make available is structure to that. If you want to have an if statement, you have an if statement, you have a conditional, and you have a block of code that will run. The compiler is going to take care of checking your conditional, making it into something that can be compared against 0 to set a flag, and then based on that flag, either jump to your block or jump to the end of your if statement. Like that is all going to be taken care of for you by the compiler. Bingo sprango, we have an if statement to reuse our terms from last time. So that is a very convenient thing as a developer. You can make methods, you can make classes, you can make types, you can make functions, you can make loops, as you said. All of this falls under the umbrella of structured programming. Now, concurrency is back to the Wild West. You want to run something on a thread. Well, you tell the system, hey, I want to make a thread and I want this work to run on it. And if you're writing your own thread, you have an infinite loop in that thread to kind of continue fetching work. So that way that thread like continues being useful. And that's something called an event loop. And you have to build all that out yourself. And if you make mistakes, you make mistakes. So the compiler is not going to know. The CPU is not going to know. It's going to think it's doing what you told it to do. So it's just going to go ahead and do that code on a different thread. And that will run in a separate queue, maybe. It's not even guaranteed. So what structured concurrency brings to the table is a set of rules and a set of primitives that you can use in the language that allow you to get concurrent code or concurrent operation relatively for free. However, it's in a more limited way. Like in assembly, you can do absolutely whatever you want. You can jump up 2 lines, down 7 lines, whatever you want.
Sure.
And that may be freeing, but it's also like ripe for disaster. So if you're limited to an if statement, you're limited to an if statement, but it's easier to kind of determine how the code is going to work. With structured concurrency, it's the same thing. You're stuck in your ability to describe what your program could ultimately fulfill, but those restraints actually make your code more clear and more assumptions can be made because it's harder to do the wrong thing like in the code itself. And therefore, the compiler can make certain assumptions about how it can optimize what it's going to do. So what structured concurrency brings to the table is at a top level, you mark every async method with async. And anytime you call an async method, you mark it with await. And instead of having a bunch of nested closures to kind of figure all of this out, you can just write linear code with if statements, for loops, everything you're used to, and it will automatically manage the context switches, the suspension points, the continuations. It'll manage all of that for you, so you as a developer don't need to manage it. So that's what structured concurrency is. If you find yourself making a manual task that is unstructured, like you're back to the quote unquote good old days, where you need to wrangle that thread yourself and manage it in what way, but you get a much nicer API. You don't need to manage a thread. You just have a task and you have a handle to that task that you can go ahead and cancel or do whatever you need to do. So that's what structured concurrency really brings to the table. And I think that will make it a lot easier for people to get into it, because otherwise it's very intimidating. It's like, oh, I have to set up a queue now, and that queue needs to like manage its own set of tasks, and I need to pay attention whether I want to synchronously access it or asynchronously access it. Like there's a lot there, even though that's like a grand simplification of threads and locks and semaphores and all that. So this is yet another simplification that seemingly takes away powers, right? But it grants more powers because you have something structured to work with, and you added some organization to the chaos, basically.
Okay, cool. Yeah, and I think along with that, you kind of mentioned something called a context switch. What does it mean to perform or have a context switch?
Yeah, so a context switch is when you tell the system, basically, I want to switch from this thread to that thread now. And the system has to coordinate like the threads as an atomic thing. The threads have their own stacks. In fact, the CPU can swap out threads at a given notice with their entire working memory associated with it. So you get the whole call stack, you have all the registers that are associated with it, and it will just pause what it's doing and say, okay, we're working on this thread now. And that's how your system works, basically. Like when you need to run multiple programs and you have one CPU and one core, it has to context switch. Right. But for the most part, now that we have multiple cores, like the main cores can be left to the foreground app to do what it needs to do, and you can have relatively few context switches, and that's where things start to work well. Now, when things don't work well is when you have to context switch constantly between two or more threads. So you do a little work, and then you do a bunch of work to context switch, do a little work, do a bunch of work to context switch, and everything starts to slow to a crawl. And that is the problematic part of like things like thread explosion, where you end up with way too many threads because you were synchronously accessing them and GCD kept making more. And context switches like become very common in those scenarios, but they can still happen with async await. Like it's just something that can happen, but you can manage that a little bit more easily, because if you are just using Swift's async await system, then you are probably not going to have very many context switches, because it doesn't need to context switch when it switches what it's doing. So basically what the async await system does in Swift Concurrency is it will have its own thread pool, but it's going to maintain one thread per core. And if you overuse those resources, you overuse those resources. That said, it can make certain assumptions about your code because you are using structured concurrency, and therefore it can organize your code in such a way where nothing will ever block any other code. And that is a great thing because then you don't need to switch threads to work on something that needs to be done in a serial manner. So for instance, if you have a resource that you can't have multiple cores accessing at the same time, like there's a protected resource there, then Swift Concurrency will just make sure that no two cores access it at the same time, even if it's running it on core 1 and then core 5 and then core 2 and then core 4. Like it will hop around as it wants, as long as those happen one after another, basically. So it can go ahead and switch what it's doing without switching an entire to an entire thread. So it can just take the part of the call stack that's related to what you were working on and like store that away for continuation later as a suspension point, and then bring in some other piece of work and just add those methods to the call stack and let that piece of work continue. So it can very efficiently kind of manage this, which makes it very convenient to use, like when we're so used to GCD and things like that.
Okay. So, yeah, okay. So, I mean, because this is sort of, I suppose, meant as more or less a replacement of GCD, it does all of that same stuff. It can do context switching. It, I guess, in this case, it will prevent thread explosions, which is a problem in GCD. It's just doing all of that more efficiently, right? If that makes sense.
Yeah. So remember we talked about that special thing called the main queue.
Right.
The main queue still exists. It didn't go anywhere, and it is fully separate from Swift Concurrency's thread pool. Like Swift Concurrency will have a thread per core, and then there's also the main queue, and the main thread and the main queue and the main actor, whatever you want to call it. It's the same resource, and there's nothing we can do about that. So the only way you can really shoot yourself in the foot with context switches in the new Swift Concurrency system is constantly switching back and forth between the main queue and an asynchronous task, basically, that can't be run on the main queue for whatever reason. So it will do its best to prevent this from happening, and we can talk about a little bit of that, but it can still happen. So that's where if you are making unstructured concurrent tasks, then like it will happen. So just be careful not to do it too often, and you should be fine, basically. Okay,
cool. Something that I really enjoyed with that very first video in the developer Meet Swift Concurrency kind of collection was in the, I think it's the Meet Async Await. It talks about how I think it's probably maybe having to do with context switching, maybe not. And we talked about this last week, but I'm kind of bringing it up now so that everyone can hear. When you have a task that like needs to be suspended, right? Like you have maybe a network call that's going to go fetch some data, and you want to perform some closure after the data gets sent back to you or whatever. You've got this kind of intermediate amount of time where the thread's potentially just kind of going to be doing nothing. And so instead of, I think, Grand Central Dispatch kind of giving that queue's amount of resources to some other task, Async Await will give it back to like the system, and then the system decides sort of the best place to use those CPU resources. Is that kind of right-ish?
Yeah, that basically makes sense to me. So you let the system take care of it, basically. It's not really the system. It's still your program that's taking care of it. It's just the library that you are bringing in, Swift, that is doing it on your behalf.
Okay. So, another one I wanted to ask was, Async Await is not using GCD under the hood, is it?
It has to.
It does. Okay.
Yeah, so it has to coordinate with GCD to a certain extent because GCD is using the same resources as Async Await. Okay. So if you do look at the debugger, you will see like it's related definitely, because it has to have the same underpinnings, because GCD has hooks into the kernel to actually communicate and schedule things efficiently that it can't do on its own, basically. And that's why a third-party dispatch or a third-party GCD, even for Linux, although available, was not nearly as good, because it could not make those same hooks into the kernel. So Swift's async await makes those same hooks, so it uses GCD's entry points for that, and that's why you will see similar names, and you'll see queues that look like they might be used for that. I think they're named something along the lines of I completely forgot, so I'm not going to even attempt. But you will notice if you put a breakpoint in an async method, it's going to have a very special like name for the thread and for the queue, and that will be like the way you identify it. But it is different enough where if you are using Swift on Linux, for instance, it's not using the same GCD that you're using on the Mac, and it can kind of do things more directly because of that. But there are benefits to it being tied to the same system, just like there were benefits to Cocoa using all the Carbon APIs for a very long time, and still using them to this day, even though Carbon as a framework has kind of evaporated.
Right. Okay, cool. Yeah, I think this is a good one. What's the difference between concurrency and parallelism?
Yeah, so concurrency is all about being able to do work that saturates all the resources that you have available. So if you have two completely different tasks, those two different tasks can run concurrently because they don't kind of influence each other. Parallelism is trying to get the best bang for your money by doing as much work as possible all at once. So you as a developer need to think about how to break up a task into something that can run in a concurrent like situation, and that is basically the difference. So Swift Concurrency provides almost no tools to do parallelism. It provides all the tools to have a concurrent workflow where if you have separate actors, those actors can all run in parallel, but you need to think about how to make it parallel, if that makes any sense. You don't need to think about how to make it concurrent.
Right. Yeah, okay. So this is probably again a contrived example, but like how many cores do we have on
10, I think, on the
10.
Mac.
Okay. So you're saying, if I want to have some concurrent work, that's all done for me, but I have to do the work and say, okay, I want to put 10 pieces of work on each, or one on each core. That is parallelism, and that's not handled for me, basically.
Yeah, you need to think about, okay, how am I going to split up this work? Am I going to use actors, or am I going to do it this task groups, or whatever you're going to like contrive to get that done? You still need to design that work, and you can still shoot yourself in the foot by doing it wrong, basically. Just like you can shoot yourself in the foot by doing the math wrong in a normal like structured programming context. Like you can still write bad code, but you can't. It makes it much harder to abuse like the threads and the locking mechanisms and getting into deadlocks. Like all of that, if you only use Swift Concurrency, you're good, right? It takes care of all that for you. In fact, there are a few like gotchas, and I think in one of the presentations at WWDC they go over this. But basically, don't use GCD stuff inside of Swift Concurrency unless you're switching to a different queue asynchronously. Like that's fine because you are going to a different thread. That's a context switch. But you're not stopping the current thread. You're letting that one continue. So you're just kind of scheduling work. So it's not really a context switch because you're not stopping what you're doing. You're just scheduling work to run on a different thread, which may be awake or may not be. But that's not your problem. So that's totally okay. Using semaphores, not okay, because that may block the current thread indefinitely. And the only way to wake up the current thread may be from a different thread. So you can get into a deadlock super easily with that. If you are locking a resource and then unlocking a resource using like an unfair lock or an NS lock, totally A-okay, as long as you lock it and unlock it in that same unsuspended, like don't have an await in between your lock and unlock. That will be disaster. If you don't have an await, then you are guaranteed that whatever work you're doing will continue because it's still a thread under the hood. So that is okay. If you can avoid it, though, you generally don't need to use locks and stuff anymore if you can use actors instead, because actors take care of making sure that all access to it is done in a linear fashion. So this is really neat because you don't need to put in anything to kind of get this behavior. In the actor, you could just use the methods as if it were synchronous code. But if you call into the actor from a different actor, even of the same type, it's going to make you put awaits all over the place. And needing to put awaits all over the place makes it safe because now your actor is playing along with the concurrent system, right? You are hopping, you are suspending the actor and then continuing the actor at a later point with more information once the await gets back and stuff like that. So actors take care of all of your locking needs, basically, by giving you a higher level abstraction. Why do you need the lock? Well, we needed the lock because we have a resource like a counter that we wanted to make sure always goes up atomically, right? Or if you have something much more complex, you have a chat like log, and that chat log needs to be like completely self-contained, and everything needs to come in order and stuff like that. So that is something that you can represent with an actor. It's a reference type. It does not have, what's that called when you can say it's a subtype of,
subclassing?
Yeah, it does not have subclassing. It's not a class, it's an actor.
It's not a
no
class,
sub-actoring,
right?
no inheritance, that's the word. Which it actually had very early on, and it was removed because it could always be added later if we really need it. So no subclassing for actors, but they do make for a good reference type replacement for all your concurrent needs. That said, in the current world of UIKit and AppKit and SwiftUI, there's not much in terms of like an asynchronous context that's just ready for you. So it kind of makes it a little awkward to use a lot of these Swift concurrency types until Apple updates all its frameworks to be asynchronous. Once everything is asynchronous, you don't need to care about anything at all, and that will be a magnificent, wonderful, magical time where we can just put async all over the place, and your UI code can run on any thread at that point, right? It doesn't matter because it's all synchronous with itself. So that is the key to what makes this like tick. And without actors, you don't have that primitive that can allow you to build upon and do all this, right?
Yeah. Okay, so with actors, I don't know if you ever taught this, but I'm fairly sure it was at Lambda. We had a project where we made like a cache class, and it was basically just a dictionary, but we kind of wrapped it into this class. And what we did was we had a specific thread a dispatch queue that we created for that, and made access to that always running on that queue. I think it more or less performed that same sort of role to make sure that things were essentially atomic within that dictionary. Yep. So actors are basically that, except that instead of only running on that queue, it's still atomic, but it can run essentially on any queue. Is that right?
Yeah, so every time you had to do dispatch-queue.sync there for that cache, you basically had a context switch. Because you had to say, pause everything, let me jump to the thread where... and GCD would try to be smart about this. If it didn't need to jump to a thread, it wouldn't. But it would essentially jump to a different thread to get that work done, update the dictionary or read the dictionary. And then it will go ahead and come back to you and say, like, here is the value you were looking for. And then from that point forward, you can go ahead and return that. So now with actors, you don't need to have that queue, and you don't need to wrap anything in a queue. All the methods in the actor, they're not async. Like, they're synchronous code. You access the you access your dictionary, or you read your dictionary, or set your dictionary, whatever you need to do. But when you call into the actor from an external executor, which is basically another actor, the main actor, whatever context you're in, you need to say await. And you need to stop what you're doing to get the results from there. But await in that case does not mean that you are context switching. It just means that you are suspending yourself and waiting for the result. And when the result is available, you will be resumed and continued from that point forward. So it's a very lightweight way of switching back and forth. And it is still heavier than locking. Like, you can write a more efficient locking system, but you need to remember to lock everywhere, and you need to remember to use the right kind of lock and not forget to unlock, and make sure that you didn't switch in between your locks and then end up in a deadlock situation, right? So you can do this better yourself, but you can use a marginal amount of extra resources and have the system do it in an overall better way, right? Because they can coordinate things a lot better than you can coordinate things between your caches. Like if you, say, had multiple of them, right?
So, sorry, continue. Now I'm, okay. Continuing on with that then. So it's basically, so you're awaiting on the actor, even though nothing in that actor is async, you're awaiting on it because it's essentially acting like a lock where something else could be accessing it in one way or another, and you're just waiting for your turn to access that. Is that essentially what it is?
Yeah, but instead of actually locking the resource, it just doesn't access the resource until it needs to access the resource again. So that's the wonder of all of this, is because the compiler can make certain verifications ahead of time, it can not need to lock anything. It doesn't need to switch to any threads. It can just run the code, and if something else accesses your cache at the same time, that will just be put on pause until the first thing finishes. That's basically it. Whereas if it doesn't need to be put on pause, it will just run right away, right?
Okay, cool. So what about, do you, okay, so let's say you've got like a serial queue and you want to replace that with an actor. Can you do that? What's the deal with that?
So this is where caveats start to come in, right?
Okay.
So we have the very first version of Swift Concurrency to work with. And there are a lot of like nuances that you may need to be aware of now, but may not need to care about in the future. So if you're adopting this now, this is something that you should know. Basically, actors maintain that all access to it is in a synchronous fashion, right? It's as if you were on a single thread that you owned for that actor, and everything was like determined to happen in that order. That said, reality is a little different, and for specific downsides of GCD, Swift Concurrency has tried to make things a little bit better. So one of those downsides is something called priority inversion. So say you have some high priority work, right? You can say, I want to dispatch this with high priority, and it will go ahead and run at a high priority. Now, if that high priority work is locking with low priority work, the low priority work also needs to run to unblock the high priority work. But if there's no threads available because it's all blocked off with high priority work, the low priority work will never run, and therefore you have a problem. Even though the low priority work may have been dispatched first, the high priority work gets to run first, and therefore you have something called priority inversion. You have like the set of priorities got swapped at some point, and now your system has come to a grinding halt and you have issues. This is why when like telling people to use GCD for the first time, you basically tell them never use background queues, because you are like giving up all power and control that you are aware of to run at different priorities and stuff like that. And it's tempting to say, hey, this is user initiated, so I want this to run faster than this background task. But if you don't understand what can go wrong with that, you can really shoot yourself in the foot. So it might just be better to make your queue and have that be at the same priority as every other queue you make. And that won't be the best code that you can write, but it is definitely the easiest code that you can write. Swift Concurrency gets around this by doing something a little bit different. So instead of having serial queues where it's first in, first out, you still have a queue of stuff for the actor, but there are no guarantees that what comes in first is going to be the first that runs. If you schedule a bunch of low priority work and then a piece of high priority work, the next thing that's going to run is the high priority work. It's just going to skip the line. And the only way that it can skip the line is by managing its dependencies accordingly. If it depends on any low priority work first, that low priority work will run right before the high priority work to actually get it going. So it manages all of this for you, but that means that things are not first in, first out. So It is not the same thing as a serial dispatch queue. For the context of our cache earlier, it doesn't matter, right? Like if you access the cache from one thread before the other thread, it's not really going to have that big of an influence. That said, if you are hooking into async await stuff from, say, a collection view delegate, that is going to cause utter chaos because the collection view delegate is expecting things to happen in a very specific order, and the user is interacting with it in a very specific order, and events get queued up in a very specific order. If you've ever noticed your computer slow down, you can click in like 5 different places, and those clicks, once the computer catches up, will happen in that exact order that you did them. And this is not the case for Swift Concurrency. So you are going to end up in a situation where those clicks, they'll happen not in the order that you made them, which is a disaster. So that is one thing that you do need to keep in mind with actors currently, is although you can only access the actor from one context at a time, the order in which you dispatch those, like with task, for instance, is completely arbitrary. One trick around this that I've done is if you have, you can set up, for instance, an @main actor kind of dummy type, and that @main actor has a single property, the last task that ran, and a single method, run an asynchronous task. And when it sets up that asynchronous task, it just awaits the previous task that ran. And the previous task that ran or the task that you're making gets set to the previous task that ran for the next one. So you're artificially making a linked list, basically, that will force things to happen in the order that you're dispatching them, which is, I think, a desperately needed thing that should have been included. But they probably didn't want to include it because then everyone's going to rely on that, and that is not the Swift concurrency way, basically. So they're leaving everyone to their own devices, but only those of us who really understand concurrency are going to come up with that solution at all. And you can also do this with an async stream if you want, because that will also encode the order of inputs. But you're back to that same problem of needing to know about concurrency to use it effectively, which is problematic. So if you do want to use async await and you do want to use actors, just remember that they are not serial. That is the law of the land. They will not happen in the order that you're making them. So therefore, it's something that you do need to keep a track of.
Cool. Awesome. Yeah. Okay. So just as a comment here, I think that's really interesting that, like you said, they had inheritance and then they kind of took it out, and it's already, just from the very, very little that I've used async await, it is incredible. So I'm super excited to see kind of where it goes in further iterations. This feels like the first kind of API in a while, kind of thinking about Combine and Swift UI that feels super fleshed out from the get-go. So that's exciting.
Yeah, and it's still being constantly improved upon. So I both encourage and caution about keeping up with all the what are those called, the Swift evolution process. And I encourage it because you can learn more from that about how this all works than you can from the documentation afterwards, because that will go through the motivations. It will kind of lead you through using this new thing called an actor that's existed for a long time in other contexts that are way more computer sciencey. It will introduce you to that topic, whereas the documentation is gonna be oh, this is an actor, which it assumes you know the foundations already. So I encourage it in that sense. I discourage it in the sense that things change, and unless you keep track of it, you are going to be a little confused. For instance, I thought actors had what was that called again? The subclassing inheritance. And I I can just make this an actor kind of tree, and I'll inherit. And I'm like, why is this not working? So I'm so confused because I read it that way and it got stuck in my brain that way. And I never read the follow-ups as they kind of made revisions that said, oh, there's no inheritance, by the way, now. We pulled it out for various reasons. I was sad because I made my grand plan in my head over 2 weeks to use inheritance with actors, and now I had to do it the scummy way of having instance variables in each of my subtypes instead of common classes. Horrible. But that's the lesson that I learned, is if I'm going to keep up with that, I need to keep up with it, and I can't just take the shortcut of just reading it once and then be like, I know this now. Yeah.
I've only used async await in Vapor, and I was kind of relating to Dimitri, wow, this is really easy to implement and everything. And Dimitri said, well, it's not so much in a normal iOS app, and it kind of sounds like a lot of that has to do with, UIKit and all that, not having implemented async await itself. Mm-hmm. But in the context of Vapor, it's been amazing. So I know this answer, but one of the questions that we have here is, how is async await different from using event loop futures, promises, and the rest of SwiftNIO?
Yeah, so when you're writing a server application, you are fully concurrent, right? You want to use as many threads as possible. You want to saturate the system as best as you can. So SwiftNIO is an excellent framework to do this. It basically maintains a thread pool. And every time I say thread pool, it's not like a pool in your backyard with a bunch of thread spindles on it. When I say a thread pool, it basically is a set of threads that are available, like an actual Swift set. And anytime you need a thread, you just ask the pool, hey, can I have an available thread? And it will say, here's one of my available threads, and now there's one fewer in there. And then when you're done with your thread, you say, hey, thread pool, let me give you back. And then you pulled together all that, all those resources. This terminology is used all over the place in computer science stuff. You might have them with an auto release pool, where you basically put objects to be auto released. You might have it with a buffer pool where you, instead of making new memory buffers, you just reuse the same ones that you've made. And you just make new ones as you run out, basically. And that's what GCD does. When it runs out of threads, it makes new threads, basically. So everything has these thread pools, and SwiftNIO will put an event loop on each of them, which is a fancy term for an infinite loop that will just wait to pull events, and it will sleep if there are no events to be pulled. So SwiftNIO is a fully concurrent system. Async await comes super naturally to it, because although it uses a different thread pool, and although they say the performance will not be optimal while they're making this transition, they encourage everyone to switch over to async await as soon as possible, because it's going to make everything better in the long run. And as you've seen directly, what you had to do in SwiftNIO is you have an event loop, and you basically schedule work on top of the event loop by mapping to more work. And then that more work will map to, might return a future, and then you map to more work on top of that future, and so on and so forth. And you end up with this beautiful and at the same time hideous pyramid of either closures of maps and stuff. And if you're good about it, you can organize it into a flattened pyramid, where instead of pyramiding on top of the futures within each map, you kind of realize that you can flat map to another future, and then you can chain the map on the original one. So you end up with a flatter kind of system. But Swift kind of freaks out with this if you get one thing wrong, because it has no idea what the types are. It's kind of following along with you, and if you make one mistake, it's you're assuming this is a string, but it's definitely not a string. So something is wrong. The compiler has no idea where to tell you where the issue is, because everything is interlaced, closures and stuff, and it is chaos. Swift async await makes this awful chaos into something absolutely beautiful, because you just have linear code at this point with awaits, and it is magical. So Yeah, if you are in a server context, this is the best thing you can do. And this is why I was saying it's going to take a few years for Apple to move all of their UI frameworks over to something like this, but it's not unheard of. Like BOS, which is an ancient operating system that Apple actually considered buying instead of Next Step to be macOS, basically had a new thread per window. And that was an excellent way of kind of keeping every window concurrent with each other, right? But they didn't really have the tools to make that work efficiently, nor the computers that had multiple cores, right? It was just one core computers at the time. So they had to context switch a lot to make that work. But nowadays, like, that is totally conceivable. Every view can be its own, like, actor, right? And it's not possible at the moment, but it could be possible if Apple were to make the frameworks to kind of get there. And SwiftUI is kind of leaning into that. There's like .task for the view itself that will automatically get canceled, but buttons and stuff, they don't really have like when the action gets called, you need to make your own task, and that feels a little messy. And it will be really nice once everything is in a fully async context for that to be much more seamless. But everything needs to kind of jump on board for that to work super seamlessly. And until then, it's still a little messy.
Okay, cool. Yeah, it has been so, it like on the level of life-changing for the Vapor work that, like Dimitri said, if you've got, I mean, oftentimes you'll want to like get something from some other API, or you're getting some information from the client, and then you have to save it in the database, and that's a future, and then you want to map that to do something else, and you're flat mapping it again, and it's just this absolute cone of doom, like Dimitri said. So having, and you know, you
have to learn that. You have to learn how to write that cone of doom, and if you don't, like, you're just like staring at your methods like, well, okay, I got my thing, and then I do the how does this get out of the function? Yeah. Like, you get so confused so quickly unless you learn how to do this. And once you do learn how to do this, async await is like so easy, and it's like wonderful. Yeah. Even though, like, if you're just coming from this, like, from the get-go and you'd never used async await before, it might still be like, I don't know how to do this. So like, definitely from one transition to the other, it makes it way better. So I hope from the other transition where you don't have any server knowledge, it can equally make it better, right?
Oh yeah, I think to me, I feel like it would lower the barrier to entry to learning Vapor by a ton, because like you said, type inference basically doesn't work within, you know, multiple kind of futures and flat maps and everything. So you mess one thing up, it's just like, I can't exactly remember what it says, but it's like, it can't infer the type. Yeah, in whatever context you're using. It's just like, it's a nightmare. It doesn't give you any fix-its. It doesn't give you any help as to like where the issue is. Kind of it like onto the very early days of SwiftUI. It's just like, here's an error. I don't know what the issue is. So having this, it makes the code and hugely more readable. It's crazy. So in that case, it's been awesome. So one of the questions that I had was, a lot of the async await code that I was converting over was very linear, and it was just kind of like, you know, here's some information, save it, or here's some information, send it back to the client. But then I was getting into like fetching multiple things, and I was dealing with loops, and so getting into more of those like tasks and task groups. So like, well, yeah. Will you talk about tasks and task groups a little bit? You mentioned that a little bit in structured concurrency, that it's kind of diving back into the Wild West of unstructured concurrency, right? But like, what, I guess, why do we have to have tasks within something like, or a task group within like a loop, if that makes sense?
Yeah, so as I mentioned, tasks are unstructured. When you make a task, it doesn't pause anything. It just will go ahead and run that code, maybe at the same time as your code, maybe at not, and there are some nuances there. And it's a completely detached task, not detached, it's a completely unstructured task that is not connected to the current context that you're calling in at all. What do I mean by this? Well, you can create a child task by doing something called an async let. And an async let will basically create a future under the hood. Like from Swift's point of view, it's still a type of string, right? Or a type of whatever object that you're getting back. Async let my object equals fetch object. But it's not going to run it right away. And you need to await your object to get the result. So you can call a bunch of async lets one after another. It's not going to run any of the code, or it might start it in the background, but it's not going to run any of the code right away. It's going to let you kind of schedule all that, and all that will run at the same time. And then you can go ahead and make an array or a tuple of that and await that tuple and get all of it back at once. Like that will kind of, or get it in the order that you need it. So that is one way of going about that. Okay. Now, if you use a task, this is probably not going to work in the Neo world because it's not going to pause for your task. It's just going to kind of run your task sometime and do something. You can get a handle back to your task, and you can await that handle to get the value. So await myTask.value, I think it's called, and you'll get the results back. But if your current context is canceled, it's not going to cancel your task by itself. You need to call myTask.cancel if you want to cancel that. That said, it is called within the same actor executor than the parent that you're the context that you're writing in. So if you are at main actor, for instance, and you make a task, that task will run by default on the main actor. Any access to the main actor on that task will not need awaits, which is really nice. If you are in an actor and you make a task, any code in that task that accesses the actor will not need an await, which is nice. Mm-hmm. That said, if you do this from the main actor, you're not actually switching to a background thread. You're just doing the work on a next run loop, right? And it's not even that. It's running it maybe on the next, maybe after another task that you schedule a little later. Like there's no order to it. So do keep that in mind. So that's task. Task dot, what's it called? They're detached. Task dot detached is the same thing as a task. So you can't cancel it automatically and all that. You still get a handle. You can still do what you need to do. But it is guaranteed to just run concurrently with your current code right away. You want it to run right now. So it will go ahead and do that. So if you put a breakpoint inside there, you're going to notice it's instantly on a separate background thread. And it is no longer on the main thread. And that is what that will do. So it kind of breaks away from the current actor context, which means that if you access the actor, you need your awaits in there. Mm-hmm. So that's the difference between a task and a detached task. That said, neither of these are child tasks, and this is something that I got wrong listening to the WWDC talks. And you need to cancel them yourself if you want to. So they are purely making an unstructured task that will run when it runs, but you have a little bit of control over that. So that's nice. Now, a task group is kind of the best of both worlds. You end up with child tasks that automatically get canceled. You end up with parallelism because you can run multiple things at once, but you are staying within the confines of structured concurrency. So it all kind of works together. A great benefit of this is if you have 17 things that need to run, those 17 things may not run in order, but the results will be in order. And this is an amazing thing because if you've ever tried to use promises and you needed like the results that you get back to be in the same order that you dispatch them, it was absolute chaos. To get that right, you needed to basically have an array that you pre-made to be the right size and then keep the index for each of those things and then replace the entry in the array with your results as you got them. And then once all of that is good, then you dispatch to the next future and say, hey, everything is ready now. You can now start consuming it. Whereas a task group will make something called an async sequence that will be in the same order, but it will basically only let you proceed as stuff is available at the beginning of it so that we can proceed in linear order. And that is very important because it basically means that you maintain the order of things that you put in for things that you get out. And you can maintain them inside of a loop and you end up with like very clean code as a result. And it's not nearly as chaotic as it could have been, which unless you've seen the could have been, you may not appreciate fully. because it still looks like a little bit of busy work for the task group, but it is much better.
Okay, so that maybe answers my question of like the actual code that I was wondering about. I have a task group that within the group I'm looping through an array of items, and then in each iteration of the loop I add a task. My question was, and I was looking at some tutorials of this, is they ended up like, for example, say that I wanted to append the result of whatever that task was to an array. The whole reason that you don't append it within that task is because it could be out of order, and so then you like go through that async sequence and it will then append whatever the result is in the same order that it came out. That's the whole reason that you do that.
Yeah, basically.
So if you don't care about the order, could you just append within the task itself?
Well, if you don't care about the order, you don't really need to use a task group, right? You can just make a bunch of tasks, save their handles in an array. Like that will all happen synchronously. So in a tight loop, you can just make a task, get your handle for your task, save to an array, right? And then at any point forward, you just await each of the tasks in your array, and then whichever one happens to get back to you, it happens to get back to you, right? Or set or what have you. So
you don't even need a task group in that case.
Yeah, the task group is really when you want things to stay in order, and that's where it will really benefit you, because it's hard to do that otherwise. And combined with an async sequence, which I think I'll get into now because it's a really cool tool that many people may underestimate. So basically, it allows you to have a for loop where you have like a for await basically. And you just want the next resource that's available. Task groups give you an async sequence, which is super neat because then you set up your task group that finishes instantly. It didn't do any of the work yet, though. Okay, so then you have your for loop, and you want to process everything that you just submitted. You're going to wait the first entry, and once the first entry is available, it will give it to you. And then you can do whatever you need to do, and then it goes to the next entry. And if that one already became available, it'll just instantly continue. Once you get to the fourth entry and that one's not finished yet, it's just going to wait and let you work on something, let the system work on something else while it becomes available. And then once it is available, it'll continue. So that makes it really easy to do things in order. Now, async sequences, where they become really powerful, they're basically lazy operators like map and stuff like that. So you can go ahead and transform sequence from one type of resource to another just by using map. It's a sequence, right? You can use first or max or whatever kind of operators you were used to, contains, and that will go ahead and wait for the resource to be available and make it available. The ultimate kind of async sequence that I don't think is ever talked about is an infinite sequence. Like this can always just have new resources come available when they're available, and they might not always be available. So you can have a for loop that is seemingly an infinite for loop, right? There's no count to your sequence. It'll just keep on getting events, whether those are from maybe a server connection where it will give you new resources that come in. That sequence can run infinitely. Now, that sequence can also be canceled from outside, so it will stop if like the network connection dies, or if you click a button that says stop. That can cancel the sequence. That's totally fine. But otherwise, or it can cancel the task, which will cancel the sequence because it's a child task. But otherwise, you can have basically a listener that will go ahead and do stuff. You just structure it as a for loop. This leads directly into like combine and all sorts of things that we're used to in an app context. Well, like how do you create a chain of events? Well, you can use an async sequence to listen to that chain of events and notifications that might come in, button presses, what have you. It's just going to take a very different way of structuring our UI code to kind of like work with this new system, but it is definitely possible, and it makes it a lot cleaner once it is kind of like fully wrapped over. So that is like what I'm super looking forward to. And I've already written a bunch of like helper libraries for async sequences, because you can make your own sequence that transforms stuff from one type to another, or accumulates like a bunch of ints from the network to make a packet. And then that packet can be transformed into an object, and then that object can be transformed into whatever you need to do, like a chat history or whatnot. So they are very composable, and the building blocks are not well documented at this point, but they are pretty easy to get your head around, and that's why I think they're pretty darn cool, if I say so myself.
That's awesome. So I guess just to clarify, and I'm sure it's the case, but if you do have that sort of infinite async sequence, it's not like it's sitting there actually running all the time. It's very much like Notification Center, where it's just listening in, and as soon as it grabs something, it'll run it, and then it's not like blocking the thread or anything. It's just kind of sitting there suspended.
Yep, exactly.
Cool. That's awesome. That's super cool. Another thing within tasks and task groups is, can you capture self? Because you're using a closure, so can you capture self safely within a task?
Yeah, so capturing self follows a fair amount of rules. Basically, it only mentions reference types, or it's only a problem for reference types, never value types, which is why SwiftUI doesn't make you bother with this at all. But the times you can capture self are limited to when you know that something will run once and it will always run. And once those two guarantees are made, you can capture self, because you are never going to run into a cycle, basically, where that closure will be kept around longer than the handle that you're keeping on it. Now, that said, tasks are a little special, because if you await in a task, that task will pause, basically, but self will still be captured. So that task can be a very long-running task, maybe an infinitely running task if there is a for loop involved. And that may be something you want, or it might not be something that you want. So if you do decide to weakly capture self in a task because you know it will take a long time, or it will be alive for a long period of time, then you absolutely do not want to guard let self equal self within the task. Because if you do that, then you've made a strong reference to self immediately after you made the task, right? The task runs immediately. It's not like it's going to be saved for the future. So your task runs immediately, and now you have a strong reference to self that, even though you marked it as weak self, you now have a strong reference that's going to stick around until the entire task is done. Which, if you have a for loop that is waiting on a sequence, that may be in a very long time, which may not be what you want, and you won't be able to automatically cancel things because everything is holding on to each other, right? So that's where you maybe don't want to use self, capture self strongly. And you want to weakly capture it, and make sure you do not guard let self equal self afterwards. You want to keep that self be weak the whole way through. Otherwise, it's gonna be pointless, because it's gonna run right away, right? It's not gonna wait to run your task. It's gonna run your task right away, and then once that self is captured strongly, it's gonna stay strong until it's done.
Yeah, okay, that makes sense. My follow-up was going to be, can you just leave it weakly captured? And yeah, it sounds like you can.
It might work to guard let self within a smaller block of code, like an if statement or a loop. If within the loop you capture self, then once that loop iteration is done, self is no longer captured. And then once the next loop iteration starts, self might go away, and then at that point you can cancel yourself, right? So that is another way, or you can break out of the loop. So that is another way of managing that well. Just don't guard let self out of muscle memory. It's not going to help you.
Right. Yeah. Okay. I think I kind of have one. Well, at the very least, one kind of task group related question. So it kind of seems like task groups more or less will fulfill, because we're kind of asyncing or awaiting on our task group. It kind of fulfills the same purpose as a dispatch group, or something that you want to, in my example, I have this task group and I'm running through an array of things and awaiting in that. So it's all asynchronous, and I don't want to run anything below that until the entire array has been run through, right? Does that make sense?
Yeah.
What I'm trying to explain? It's like a dispatch group like that. So do I have to have a task group in order for that to happen? Or like we were saying, could I just have a bunch of tasks that I'm awaiting and still have the loop finish all the way before it runs code below it, if that makes sense? I'm not quite sure.
Yeah, so if you don't have a task group, you need to manage that yourself, because you have a bunch of tasks that unless you await on those tasks, they're not just gonna you're not gonna pause yourself, if that makes any sense.
Sure. Yeah.
Whereas a task group, you can await on the sequence as a whole to get a brand new array of results, and that's a concrete thing. So you can await on that if you want to not process things as they come in. If you just want to have all the results and then be done with it, you can just pass that forward. An async sequence is still just a sequence, right? So you can cast it to an array. I'm pretty sure there are a bunch of methods on it to get the whole of it. You can map on it. You can do whatever you need to do essentially at that point.
Okay, cool. So then in that case, I probably still do need a task group to kind of, make sure that things don't run after that. All right. That probably didn't make much sense. Sorry. Cool. I think that was super helpful. I don't know. Was there anything that I know we didn't talk about all of the questions that we have. Was there anything that you wanted to go over before we continue?
Yeah. So I think as a final note, Swift Concurrency is more than just syntax sugar around closures. And it's something that is quite fascinating to learn about what's going on under the hood. So if you are used to async await from something like JavaScript, it is not the same thing. JavaScript is a single-threaded language for the most part in the browser. And if you await, it is just fancy syntax for not having a tree of closures, right? It gives you a little bit of structured stuff where you can have if statements, loops, and all that without a nested doom of pyramid of my brain buffer just ran out on that sentence. But yeah, so it's not the same thing. And there is a lot going on under the hood to make it something that works really, really well in a concurrent system. But you need to still learn about how it's working. So hopefully everything that we've gone over today really helps kind of either bring up questions and make you wonder hey, I guess I didn't understand this thing just as well as I thought I did, or clarify things. I definitely want to encourage everyone to watch the 4 or so WWDC talks on this. Although their information is a tad different than what we currently ended up with, especially in terms of the nuance between what a task and a child task is. I think a lot of people got confused about that because it wasn't really clarified. So hopefully this helps clarify all that. But if you have more questions, I think we definitely could do a follow-up episode on just this.
Oh, yeah.
So if you do have questions, tweet at us at Code Completion. And we'll definitely try to assemble them. And once we have enough, we can do a part 2 on this whole thing.
Yeah. Oh, one thing I also wanted to mention, a cool part about all of this async await stuff is because it is, I guess, how would you say it? Works alongside GCD is you don't have to refactor an entire app to use it all at once, just UIKit and all that doesn't have it right now. Throw it in a single function. That's how Dimitri got me to to start actually learning async await instead of putting it off longer was, refactor a single function to use async await, and then you'll want to do everything. And it happened like that. So you can kind of do it at your own pace, which makes it nice.
Yeah, it definitely makes your code a lot cleaner. And although in some cases, with server-based Swift programming, it really is just syntax sugar at that point because you already have all the event loop threads that are kind of managing the heavy stuff. And you have a separate set of async threads that you're just barely using. In that case, it kind of is syntax sugar, right? It is making your life easier. But by doing the foundational work now, then once they switch to using those same threads, things get way better as a result. So in the distant future of Swift 6 is probably when this will happen. That whole switchover can happen. But until then, it's really easy to just use piecemeal. There are a few warning flags that you can set in your Xcode project to make sure you're not doing something stupid. Though I think they're getting automatically turned on with Xcode 13.3, so maybe you don't need to set them anymore. But it definitely does make things a lot nicer, which is super nice.
Yeah. compiler errors actually telling you what's wrong is awesome, and telling you that you're doing things wrong is great.
Yeah, and you end up with like 5 lines of code with something that would have been 20 before, right?
Yeah,
just managing all the maps and stuff.
Yep. I will never go back as long as I don't have to.
Yeah, it's definitely so freeing, especially when you're used to the event loop features and promises and all that. Yeah, never again.
No. Like I said, I'm so stoked. I hope this really does get people into Vapor and, I mean, really anything, that is outside of Apple platforms. When you're having to deal with all of that concurrency yourself, it's a nightmare. So it makes it so much easier and more readable and easier to reason about. So barrier to entry lowered is a good, it's a good thing all around.
Definitely.
So
this week's episode of Code Completion is brought to you by Not Pho. Tired of eating the same old meals time and time again? Consider Vietnamese food. You might already know of pho, but there are a ton of other flavors specific to Vietnamese cuisine that are sadly not well known around the world. This includes everything from sandwiches like banh mi, rice plates like com tam, and even the deliciously savory crepes known as bánh xèo. And that's where the app Not Pho comes in. It's a free-to-try app dedicated to teaching you more about the wonders behind Vietnamese cuisine, brought to life with colorful and interactive illustrations and animations. Learn how to make many classic Vietnamese flavors at home, but even if you don't cook, you'll know how to order like a pro the next time you visit your local Vietnamese restaurant. New since version 1.1 is the Chef Club, regularly bringing you even more recipes like avocado mango smoothies, fried rice, chicken curry, and my personal favorite, chicken beef, for the low cost of $2 a month, with more recipes added regularly. Thanks again to Not Pho for sponsoring our show. Search for Not Pho, that's N-O-T space P-H-O, on the App Store today to give it a try, completely for free. So this past week, I forgot to buy something for our mini review corner, but luckily Spencer has my back with a very neat little gizmo, a USB multimeter. So what is this thing?
Yes, so this is it. They come in many different shapes and sizes, but this is a pretty universal one. I was watching an MKBHD video where he kind of had this really cool USB-C cable that when you plug it in, it's got a little readout, a little screen right on the end of the USB-C cable where it plugs in like to your MacBook, and it will tell you how many watts of power it is drawing. And I was like, oh, that's super cool. And it got me thinking that I know that different like USB-C cables have different sort of, I guess you could call it like qualifications or kind of ratings for how much power they can draw. And it got me curious as to like, I have a bunch of different power bricks and, external battery banks and stuff. And they all claim they'll draw X amount of power and stuff. And it supports power delivery charging and all of this stuff. So I got this to kind of verify the claims more than anything, just for fun. So as an example here, I've got an iPad. And so what you do is you like plug it into your iPad. If I can find the port. So this one's got USB-C in and out, and USB-A in and out, and also I think it has micro USB as well. So what I'm going to do is I've got this kind of like black cable plugged into there's a lot of stuff here. I've got my battery bank that supports fast charging, so that's not the issue. But the cable itself, I'm going to plug in here. And it's going to say, welcome. And it's going to start giving me a readout of information. Yeah. And so you can see here, I think it's pulling 17 watts on the bottom left for you. That kind of red. Is that what it says?
Yeah, 18.3.
Okay.
And then as soon as the screen turned off, it went to 13. So like...
Okay. Yeah, okay. So like 13 to 18 watts. So interestingly, I was messing around and I have this Apple branded USB-C cable somewhere. Here it is. So just a normal one that like comes with your iPad. So I'm going to plug it into the same thing and plug it.
This is immediately way better than my method of checking. Oh, is the cable thick or thin?
Exactly, right? Yeah. And so now,
23.5.
Okay, so it's different, right? Mm-hmm. So It's kind of a cool way to verify, are the cables high quality? Do they actually charge up to the point that they would? And I haven't tested this, like, for example, on a like my MacBook or anything, but in theory, this meter, I think, can read up to 150 watts. So it's plenty for even like the big, power bricks that you get with your MacBook and everything. So it's kind of a cool device just to verify that things are charging at, potentially charging at the rate that they say they will, whether it's the wall charger, the battery bank, the cable even. You can kind of verify that with this. And that's really all I'm using it for. It's not like I'm, a technician that would do this on the daily, but it was, I think, about $15, and it was kind of a cool thing to just test. And
I think that's a very useful tool if you have like a box of cables and you have no idea like where they came from or if they're useful. This can help you quickly categorize them. Like something we did is we have a label maker, so we labeled all of our lightning and USB-C cables fast lightning, slow lightning, this or that, because like you can't tell at a glance unless you know like what the pins look like, or like if you look on the backside of the USB, you can tell if it's a fast USB-C cable or if it's a slow USB-C cable just by the number of pins. But you have no idea how much power it can deliver, as you just showed, between the black no-name cable and then the higher quality Apple cable.
Right.
Yeah, you pay an arm and a leg for those cables, but they're actually like made to not kill you, which is nice.
Yeah, they're pretty good. Another thing that kind of got me thinking was like, when, not that I've done this in a couple years, but like when I go on a trip, I'll always bring a battery bank, and I want to make sure that both the bank and the cable itself is fast charging, because that's like really the only time that I would care that it's a fast charging thing. Otherwise, it's sitting on a shelf and just it could trickle charge for all I care at 1 watt and whatever. So making sure that I bring like high quality cables when it matters, when I'm out and about and I need a fast charge or whatever. So kind of cool device, definitely worth checking out, I think.
Yeah, I think you've convinced me that is something that I probably want as well, just because the box of cables has gone large over the years. And even though I can throw out all the ones that are non-USB at this point, there's still a ton of USB cables in there. So, as always, I want to personally thank everyone for listening in this week. Please be sure to follow us on Twitter at CodeCompletion to know when new episodes get released, and feel free to tweet at us if there's ever a topic you'd like for us to dig into. Most importantly, as a small podcast, please be sure to share this with your friends and family who are also interested in any part of the process of app development. It's your support that enables us to continue doing this, and we help to grow a healthy community around everything we discuss. Once again, I want to give my thanks to Spencer, who's at Spencer C. Curtis, that's SpencerCurtis on Twitter, for joining me this week. My name once again is Dimitri. You can find me at Dimitri Bouniol, that's DimitriBouniol, and we'll see you all next week.
Bye.
Oh yeah, because it is recorded, right? Yeah. Well, it's dotting now, so maybe if you see it properly, then it's probably fine.
It's dotting for me now. If you record your screen... Oh, there we go.
It's still pink on my side.
Oh, is it? That's okay.
Yeah, like Brave, when it showed the preview, it showed it fine. And I guess if you're seeing it fine, then it's transmitting it fine.
Probably.
The joys of a ever-breaking setup.
Yes. Well, that's what you get for running an Intel machine. That's all I can say. Yeah.
So right before we recorded, I like woke up my computer and I go, like fans at full blare. I'm like, this is an excellent sign. So I like quit the big offenders first, like Safari and all that, and it was still making a lot of noise. So I'm like, okay. I grab my phone, flashlight out. I get under the desk as best I can. I try to see like in the itty bitty cracks, and like it's full matted cat hair, of course.
No.
So I went against your suggestion to like hold with toothpick or this or that. I just got the vacuum out. I didn't turn off anything. I just like sucked all the cat hair out from the bottom, and that like immediately improved things.
Yeah. I can't assume that it spun the fans up very loud if you were like sucking air that way. Does that make sense? I don't know. I mean, I guess.
Well, yeah, so I hope I didn't ruin anything by like having a live computer with a fan that slowly heated up from not being able to suck any air because there's a counter flow going on, but it did its job, and that's all I care about. It's working now,
and you got a cool new pink feature.
Exactly. And then you sent me the link, so then I was like, oh, let me check this out. And then as I clicked down, I was like, fuck. Because I realized I quit Safari on purpose. Because I didn't want it running because the fans go crazy. So I'm like, well, I can't back out now. I already clicked down. So I clicked up. And lo and behold, Safari is still launching 13 minutes later. It has gobbled up 17.78 gigabytes, 81 gigabytes, 17.85 gigabytes. It just keeps climbing.
You are a menace.
And this one doesn't even have that many windows open. I think my iCloud must be like cursed in some way. Where it's like all the tabs in iCloud kind of that, you know, that feature?
Yeah.
Okay, so I have like so many computers that my habits on each computer is just like compounding the problem.
Yeah, sure.
So even like on a fresh install, it's like Safari's already borked. So yeah, that is my life at the moment. So if everything comes like to a screeching halt, it's because Safari decided to wake up. And that's just how it's going to be, I guess.
All right. Well, it's going to be an adventure.
Yeah. My memory pressure is only at 28%, so it's not... The system is not taxed at the moment, despite Safari taking 18.73 gigabytes.
What's the max amount of RAM an iMac Pro can have? Is it 64
256.
Gigs? Oh, okay.
Yeah, they updated it in the most recent like revision to it, if you can call it that. It used to be 32, 64, 128, 256, I'm going to say. And I opted for 64 back then, which was like an astronomical price. Like, I've never paid so much money for a computer, and it lasted me like 4 years, so that's good.
Yeah.
4 years of having the best computer you can get is not bad, I would say.
What processor did you get in that?
I got, let's see.
Here, or like the core thread count?
Free, instead of commented out, this would be the doc comments, because it's at the front.
There we go.
Yep, so, I got the 3 gigahertz, 10 core Intel Xeon W. Yeah. And graphics, I got the Radeon Pro Vega 64, 16 gigabytes.
Yeah, that's great.
I don't know what any of that means. I assume the best graphics card I can have, the more windows I can have open. That's how I operate.
Probably. I mean, it has to draw all those windows, so yeah, you're
exactly. That's my
wrong.
thinking. So the more graphics I can have, the more windows I can simultaneously have open.
Oh my gosh! Remind me to never let you use any of my computers ever.
Oh, whenever Lynn asks me for help, I go over to her computer and like help her, right? And then like my habit is, I need a research thing, so I go to make a new window and then start like making a bunch of tabs in that window for that that idea, and then I'm like, okay, we need to research something else, make a new window, and all of a sudden her computer, which had like one window with like 5 tabs in it, now has like 7 windows open with like all sorts of tabs in each. It's not like I don't use tabs. I do. Like one window is one idea that I'm like researching.
Oh, man.
So it's just like utter chaos. My brain matter just like goes all over my desk. And, like, in real life, this is the case, too. Like, my desk is relatively clean, at the moment. But, like, when I'm sketching out ideas, I do it on pen and paper because, like, I guess I'm most effective with it. And it's, like, way bigger than an iPad when you use, like, those legal paper that I have, like, a giant stack of. And that ends up all over my desk, too. What's that saying? Out of sight, out of mind?
Yeah.
Like, if it's closed, I will never remember to think about it again. But if it's open, then eventually I'll cycle through it and be like, oh, yes, I was doing this. Let me continue that thought process, and it just grows from there. Any case, I'm a hot mess. So let's just get started.
All right. This, I just have to share this image because that's exactly what we're talking about right now. This is what you need to do in your office.
I just need to have that crazed like an expression for it.
Tear down all of your posters, just have like UI designs up on the wall.
I did contemplate that. So you can get paint that acts as a whiteboard.
Mm-hmm.
Like the finish comes off as like a super glossy that you can use dry erase markers on. And I really, really wanted to do it for like that wall. But then that got added, and like there's less and less wall that you can access. So one day I will have a giant wall whiteboard, and that will be where my brain matter goes, and I'll make a nice backdrop for the podcast.
There you go. Jeez.
I also want a longer little microphone cable so it can like go around under the desk and then back up. Mm-hmm. Currently, it's like on top of my keyboard, and I already suck at using a keyboard enough where I like need to stare at it, and then there's like a wire in the middle, and like I'm not a happy camper.
You're just playing on hard mode.
Playing on stupid mode, more like it. Self-imposed stupidity. Should have just learned how to type when they told me to.
Oh yeah, me too. I feel so. I took a typing test. Okay, so I was watching this YouTube video of this guy that he plays Smash, but he was explaining how he types, and he like types like, you know, WASD fingers, like gamer fingers on one hand, and then the other hand he just pecks with one finger, and he can get 80 words per minute. And so I took a typing test, and I got like 65, and I'm like, I have like okay form, but I can't even match this guy that's like doing this weird combo of. I was like, man, I had a friend in school that could type something like 110 or so words per minute in like 6th grade. I'm like, yeah, bummer.
You know how they say we're like slowly losing our pinkies and our pinky toes over time because like we use them less and less, and they're more and more vestigial. Like when I type, they like park. I just use these 3 fingers on both hands. I'm like, easy to go out of the way.
Your fingers are going to be like atrophied when you're old, just like all the time. That's awesome, dude.
That immediately reminded me. So my dad like started using a computer super late in life. So he like learned how to type when I was like 17. And he's like, where is this stupid W on the keyboard? I cannot find it. So I'm gonna be like, where is the W?
Oh, that's great.